of our chapter before our test. So we're going to do half of 3-6 today, the other half of 3-6 tomorrow, and then Wednesday we're going to review. Thursday will be part 1 of the test. Friday we'll review again, and then Monday will be part 2 of the test. And the test is going to be over everything from 3-1 to 3-6 is what it's going to be covering. But you'll see it on the review a little bit more when we get closer. Okay, so rational functions, the last little piece of the puzzle. Again, I printed the notes for you guys, so you guys have some of this already. So first of all, what is a rational function? A rational function is where we have a polynomial divided by a polynomial. So that's why we've done division, and that's why it's in this section, because it's all about polynomials, one over the other. So it's just going to be a single fraction when you see these. The first thing we're going to talk about is how to find a vertical asymptote. These are going to have both vertical and horizontal asymptotes in most cases. How we find a vertical asymptote is we figure out where our denominator is equal to 0 at. So that's going to be an undefined value that comes from the denominator. We know from talking about domain before, we're not allowed to have 0 in the denominator, so it's also going to be a domain restriction. All right, so this should be on your paper there somewhere. We're going to find the vertical asymptotes of the following rational functions, and then we'll use that to help us figure out also the domain. So the first thing that you need to do is you need to factor the polynomial completely. Now the numerator in this problem is already linear, x plus 2, so there's nothing that we need to do there. The denominator is difference of squares, so you can factor that. What does that factor to? X squared minus 4.
X minus 2
close.
minus 2x plus 2.
Yes, so difference of squares, you can just, if it's a minus with 2 things you can take the square root of, the square root of the first term is what goes in the front, the square root of the last term is what goes in the back, and then it's always 1 plus, 1 minus. When we FOIL it out, the outside and the inside will end up canceling. Now, what happens here, in some cases, you will have a common factor in the numerator and the denominator. We have both x plus 2 in the numerator and denominator. So those are going to cancel, and it's going to create what we call a hole in the graph. It's going to create a hole in the graph when we set x plus 2, what we canceled, equal to 0. So at x equals negative 2, we say there's a hole. So what that's going to look like, it's not going to be an asymptote. It's just going to be along the curve. When we graph it, there's just going to be this single value that's an open circle on the curve. And when we get to graphing tomorrow, we'll kind of see what that looks like. When I cancel it, I'm left with 1 over x minus 2. That's the simplified version of this equation. Once you have the simplified version, to find the vertical asymptotes, you just set your denominator equal to 0, and then you solve. So I have a vertical asymptote at x equals 2. It is important that you put the x equals in front of it, because this is an equation of a vertical line. So if you just put 2, you would lose a point on a test or a quiz for that. Okay, and then again, we have a hole at x equals negative 2. You can also find the coordinates of the hole. So again, the hole came from when we canceled out that x plus 2, so negative 2 is the x coordinate. If you want the y coordinate of the hole, you just have to plug that negative 2 into the red equation, the simplified one, which was 1 over negative 2 minus 2, which will be negative 1/4. And that is the y coordinate of the hole. But again, we'll see that on the graph when we get to those tomorrow. Okay, last thing is the domain. So the domain of these, we only have to worry about domain restrictions, things that came from the denominator. We know x can't be 2 because that's a vertical asymptote. We know x can't be negative 2 because that's a hole. X can be anything else. So we've seen problems like this before. How we write them in our interval notation is negative infinity to negative 2, negative 2 to 2, and then 2 to infinity. Okay, so anything from the original equation that would make the denominator equal to 0, 2, or negative 2, we say is a domain restriction. All right, and that's everything for that problem. So let's look at the next one. Again, the numerator here is linear, doesn't factor. The denominator, I've got 3 terms now. Can you tell me how that's going to factor? What multiplies to negative 10 and adds to 3? X x plus 5, x minus 2. Do we have any common factors that would cancel here? No. Nothing is a common factor. All three are different, so that's as far as we can go with it. Vertical asymptotes. Set your denominator equal to 0. And if I solve each of those, I'm going to get x equals -5 and x equals 2. So there's 2 vertical asymptotes on this graph. As far as a hole goes, nothing canceled. So there's no hole. And then as far as the domain goes, the domain is everything except for those 2 x values that we're not allowed to equal. So -infinity to -5. That's the first thing I would hit as I go from left to right on my number line. -5 to 2, and then 2 to infinity. All right, so questions on vertical asymptotes, finding a hole, or getting the domain of these functions. Yes?
Why is there no hole?
There is no hole because nothing canceled. There's no common factor here. In this one, that x plus 2 canceled, so that's what creates the hole. If I set that equal to 0, -2 is where the hole occurs. Other questions? Yep.
So the A's are just like if we were to take out our zeros for any other normal equation.
It's just like how we found domain restrictions like a couple chapters ago whenever you set your denominator equal to 0. You just have to make sure it's simplified first.
So we wouldn't have to go through like factoring it all out. We could just let it fold out like normal, like how we usually would for.
You still have to factor it, like this x squared plus 3x minus 10, it's pretty hard to figure out those without factoring part of it.
Well, that part, yeah. Like for the first one you did something to pull out the -2, but we could just lift up and solve it.
So yes, I can figure out this factors x minus 2, x plus 2, but x plus 2 is not a vertical asymptote. That's why we do this first. So you have to factor everything, and you have to reduce the fraction, which we did, to be able to find vertical asymptotes. Only after it's reduced, that denominator equal to 0 is a vertical asymptote. If something cancels, it's still a domain restriction, but it's that hole instead. Okay. Other questions? Okay. Maybe let's do one more of those real quick. You can just put it in your margin somewhere. All right, let's say, I gotta make one of these up. Insert a blank page here somewhere. There we go. All right, let's say I have this function. Let's do that. And then let's do, that's my denominator. Okay, so vertical asymptote, hole, domain restriction, let's just put it all on there. Does my numerator factor? To what? Close. X plus 3, x minus 3. Difference of squares, going to factor to conjugates. What about the denominator? What multiplies to 3 and adds to 4? Not quite. X plus 3 and x plus 1. Okay, so do we have any common factors that would cancel? Anything cancel? X plus 3's cancel. Okay, so the simplified equation is x minus 3 over x plus 1. Okay, so things that I can get from all of this. The first thing I can get is a hole. Now, if nothing canceled, we would just say there is no hole. This one, something canceled. So I'm going to take that x plus 3, what I canceled, set it equal to 0. So we can say there is a hole at x equals -3. If you want to find the coordinates of the hole, -3 is the x coordinate. And then you just plug it into that green equation there, the simplified one. So it would be -3 minus 3 over -3 plus 1. Let's see, that would be -6 over -2. So +3 would be the y coordinate of the hole. Okay, and again, we'll see that in the graph tomorrow. Then vertical asymptotes. Your denominator that's left, x plus 1, set it equal to 0. So we have a vertical asymptote at x equals -1. And then domain is everything except those x values that came from the denominator. So x can't be -3 because there's a hole there, and x can't be -1 because there's a vertical asymptote there. The domain is everything else. So it's -∞ to -3, -3 to -1, -1 to infinity. Does that make sense? Are we okay? Any questions? Okay, moving on. All right, rules for a horizontal asymptote. Yeah? The simplified version of the denominator, set it equal to 0. You have to reduce it first. Yes. Because if I just set that original denominator equal to 0, I wouldn't see that it was a whole, not an asymptote. Got to reduce it. Okay. All right. Horizontal asymptotes are much easier. So there's 3 rules that you need to know. And the rules come from the degree of the numerator, that's n, and the degree of the denominator is m. We're going to compare those 2 numbers. If n is less than m, there is a horizontal asymptote at y equals 0, and that's it. There's nothing to solve for. If n is equal to m, what we're going to do, what this little guy on the side means, is we're going to set y equal to a single number, and to get that single number, we're going to divide the leading coefficient from the top and the bottom. Whatever the leading coefficients are, we divide them. So maybe there's a 4 on top and a 2 on the bottom. So y equals 2 would be the horizontal asymptote. If n is equal to m, or greater than m, excuse me, then there is just no horizontal asymptote. Instead, it's an oblique asymptote. You can only have one or the other. Oblique is a fancy way of saying a diagonal asymptote instead of a, or it could be other shaped as well. Most of ours will be diagonal. Anything other than linear, that's horizontal or vertical, okay? All right, so examples. Like I said, these are real fast. On the next page, we're going to find horizontal asymptotes. For these, you do not have to reduce. Even if you did reduce, it's fine. It's not going to change the relationship between n and m. So you're going to first name n and m. N, degree of the numerator. What's the highest power in that numerator? 1. And m is the degree of the denominator. What's the highest power in the denominator? Also 1. So n equals m in this case. If n equals m, the horizontal asymptote is y equals, and it's an equation of a line that we're writing, so again, the y equals is going to be really important. If you don't put it there, you lose point. Y equals, and then we divide the leading coefficients. The leading coefficient in the numerator is 2. The leading coefficient in the denominator is 3, and that doesn't reduce, so that's our answer. That's it. Okay. For the one at the in the middle there, let's see, what's n? Degree of my numerator. 2. M, degree of my denominator. 1. So n is greater than m. So what does that mean? It's actually no horizontal asymptotes. Instead, it will be oblique, and we'll talk about later how to figure that guy out. Okay, so if it's asked for horizontal asymptote, your answer would just be none. The one at the bottom, what's n, degree of my numerator? 1. M, degree of my denominator? 2. So in this case, n is less than m. This is the case where it is automatically y equals 0, or the x-axis is the horizontal asymptote. Okay? All right, so we got vertical asymptotes, we got horizontal asymptotes, we got holes, we got domains, all the little pieces and parts here. Any questions so far? All right. How do we find an oblique asymptote? So let's say it's that case where the degree of the numerator is bigger than the degree of the denominator. That means you can actually divide the rational function and simplify it a little bit. So that's actually how we find oblique asymptotes. To get an oblique asymptote, we are going to divide, and the quotient that you get when you divide the numerator by the denominator is going to be the oblique asymptote. Okay. You can either use synthetic or long division. It depends what you're dividing in. If you're dividing in something that's a linear term, you can use synthetic division. If you're dividing in something that is not a linear term, you have to use long division. So let's look at this one. Okay, so my n is 2, and my m is 1. N is greater than m. So as far as horizontal asymptotes go, there are none. Okay. That means I can instead find an oblique asymptote. Now I am dividing in a linear term here, so you can use synthetic division or long division if you want to use that. I'm going to use synthetic division. I'm going to set up my coefficients. So this is a review. 1x squared, 1x, and then there's no constant term on top, so I want to put 0 at the end of it. If I'm dividing in x minus 1, what number is going to go in the box? 1, and then we just do our synthetic division. Bring it down, 1, multiply 1, add 2, multiply 2, remainder 2. You do not have to get a remainder of 0, and in fact, the remainder doesn't matter here. What our quotient is, what's in front of that remainder, is your answer. If I put the variables back in, I had an x squared, I divided in a linear term, so now I'm left with a degree 1, a linear term. This represents 1x plus 2. Stick a y equals in front of it, and that is your oblique asymptote. Okay, so it could be a line. This would be a diagonal line. You can imagine graphing it has a y-intercept of 2, a slope of 1. It could be bigger than that. It could be a quadratic. It could be a cubic. It depends what we're dividing in. All right, so that's oblique asymptotes, horizontal asymptotes. Can you guys tell me what the vertical asymptotes on this one are? Where do the vertical asymptotes come from? Denominator. So set that denominator equal to 0.
1.
X equals 1 is a vertical asymptote. So you might see problems that ask you to find all asymptotes, and this is what you would do. Vertical is coming from the denominator. Nothing reduces. Even if you factored an x out of the top there, I'm left with an x plus 1. You can see we don't have any common factors, so we don't have to worry about those or anything. Denominator gives me the vertical. N's and m's then tell you if it's either horizontal or oblique. Okay? Questions on oblique asymptotes? All right, so there's only one other kind of piece we're going to add in today, and then tomorrow we're putting all these little pieces together to get a graph of this. Ultimately, the goal is to try to graph one of these without a calculator, like you did with the parabolas and the polynomials a couple weeks ago. All right, so this is kind of an example of what end behaviors of rational functions look like. So when we talked about end behaviors of polynomials, there were only 4 cases. Both ends went up, both ends went down, or one side went up and the other side went down. Now, because we have vertical asymptotes in the middle, we have more ends. So in these 4 pictures, we've got one vertical asymptote, which splits my graph into 2 pieces, which means there are 4 ends. Each end is going to have its own end behavior. The ones on the left and on the right are going to be the same as what we've done before. X approaches negative infinity, x approaches positive infinity. The only difference is they might not be going up or down forever. They're going to be getting close to a horizontal asymptote. So we're going to say what that horizontal asymptote is. Like this one, I would say it's approaching 0. It's getting really close to 0 as I go further to the left. Or this one, I'd say it's getting really close to 0 as we go to the right. The end behaviors in the middle then, we're going to say as we get close to this vertical asymptote, it's either going up or it's going down. But here's the problem. Pictures like this both go up or both go down when they get close to the asymptote. But these ones don't. On one side of the asymptote, we go down, and on the other side of the asymptote, we go up. So we need a way to distinguish between these two. If you are on the left side of an asymptote, we're going to say x approaches that number. I'll just use like a 3, for example. And there's going to be a little minus next to it up in the exponent. If you are on the right, there's going to be a little plus. You only need these little pluses and minuses when you are next to a vertical asymptote. And then the y's, again, will be either up or down forever. So that's what we're going to practice at the end now. Looking at these pictures and trying to name the end behavior. We are also, instead of the x approaches and the y approaches with the arrows, we're going to add in, I mentioned this when I taught you before, the word limit, or the abbreviation for limit, above each of these. So let me give you an example. Let's say I wanted to look at this picture down here, and let's pretend it's getting close to 3. That's the vertical asymptote. I would say the limit as x approaches 3 from the left. So I'm at 3, bless you, but I'm on the left side of it. On the left side of 3, it's going down forever. So I would say that equals negative infinity. On the left side of 3, it goes down forever. So on the right side of 3, and again, it would have its own little limit above it, I would say that that guy is going up on the right side of 3. So that's approaching positive infinity. Okay, so this is how we're going to write them, with limit notations. We're going to practice that. That on my way today. All right, everybody got it? Okay, so let's try it. And I need, oh, I wanted my limit notation on here. Each of these should have an LIM above it. Okay, and we're just going to put equals for each of these. We're using that. Our book uses this notation, but that is not the notation you use in calculus, so that is not really very helpful. Okay, so if I'm looking at these pictures on the top right here, there are 6 ends, and I'm going to number them just from left to right, just so you can kind of see what we're looking at. 1, 2, 3, 4, 5's up there, 6 is to the side. Each of those ends, we're going to list the end behavior for. All right, the one on the left, we need to answer 2 things. If that line continued forever, what's the x getting close to, and what's the y getting close to? If this line went forever this direction, what would the x be getting close to? The x. X is left and right. It's going to go towards negative infinity. Okay, so it's the limit as x approaches negative infinity. And what's the y getting close to? 2. Okay, so often we're going to see at the ends of these functions, it's approaching whatever the horizontal asymptote is, which in this one you can see is drawn at 2. Let's jump to number 6, the one on the other side. What's x approaching on that side? Positive infinity. It's going forever to the right. And what's the y approaching? 2. That's it. Okay, let's look at number 2 now. If we were to extend that line, what's the x getting close to? It's getting close to negative 3. It's getting close to that vertical asymptote, but we need to say what side of the vertical asymptote. Is that guy on the left or the right side? It's on the left, so we put a little minus there. If I were to extend that line, what's my y, my height, getting close to? Positive infinity. Good. Okay, what about number 3? What do you think the x is getting close to there if I were to extend that line? Negative 3, but what side is it on? The right. So we put a plus. Does that make sense why that's on the right side of the asymptote? It's on the right side of that line. Okay, what's the y getting close to? Negative infinity. Okay, what about end behavior number 4 that I have labeled there? What's the x getting close to? 3 on which side, left or right? Left. And my y is getting close to? It's going down, negative infinity. The last one, number 5 up there. X is approaching this guy up here. 3 on what side? Right. And my y is approaching positive infinity. Okay, domain and range. If you have the picture, it should be fairly easy. Let's start with domain. The domain is everything except what two numbers can we not equal in this picture? 3 and negative 3. So the domain is negative infinity to negative 3, negative 3 to 3, 3 to infinity. As far as the range goes, you just look at the picture. What's the lowest this graph gets to? How low does this graph go? Negative infinity. And then does it go up forever or does it stop somewhere? Stop somewhere. What number? It goes a little actually higher than the origin. You see that point's labeled? 2/9. Do you think I'm going to have a bracket or a parentheses at 2/9? Bracket because it's equal to. We have a point there. Then it jumps. What's the next y value it jumps to? 37 is labeled, but there's values below that. 2, but do we touch 2? No, so parentheses 2 all the way to infinity. Vertical asymptotes, we already said, were x equals 3 and x equals negative 3. Horizontal asymptotes, y equals 2 in the picture. Okay? All right. So last problem of the day then, you guys are going to try and we're going to put answers up on the board. And I tried to label them with like little icons so we all are putting things in the same place. So for each of these, I want to see this notation. The limit as x approaches something and then the y that goes with it. Those are the two things that you're filling in. If you're close to a vertical asymptote, make sure you put the little plus or minus next to the number. And then see if you can answer the rest of the questions. Okay? Good? Work together? Go.
No way, no. Yeah. Where are we going? It's on the website. Yeah.
This is so close to perfect. There's only one tiny thing I would change. The U's. That's it. Everything else is good. What questions do you have on end behavior? Anything? Does this notation make sense? This is the notation you use in calculus. So if you're going past this class, we want to try to stay consistent so it doesn't look like something new next year. It's all the same stuff. All right, we're going to stop there for today. Tomorrow then, all we're going to do is put all these little pieces together to make a graph. It won't take very long. You guys will get your quizzes back. Those are almost graded from last week, so we can see those. And then you'll get your test review that we'll start working on Wednesday together. Okay? Great. All right, I'll do cell phone lotto last